Okay, so hello everyone, and I hope you all are safe and healthy. I'm Puneet Mishra, a faculty member in the Department of Physics at Central University of South Bihar. And on behalf of the Department of Physics, I take this opportunity to welcome all our guests and participants to the Indian Physics Association's DAE CV Raman lecture in association with Board of Research in Nuclear Sciences. We are very thankful to IPA and in particular Professor Vandana Nanal for providing us this opportunity to host this lecture. And today's lecture will be delivered by a highly distinguished researcher, Professor Jayaram N. Chenglur from National Center for Radio Astrophysics, NCRA-TIFR, and the topic is Radio Perspective on Galaxies and Galaxy Evolution. And thanks to IPA, this lecture is also being broadcasted live on YouTube. So at the end of the talk, we will have some questions. And so if you have some questions, please type it in the Q&A window in Zoom or in the comment section in YouTube. So before we begin this webinar, I would like to welcome Professor Vandana Nanal, General Secretary of IPA, to say a few words about IPA and about this lecture series. Over to you, ma'am.
Thank you, and thank you to our hosts, Department of Physics, Central University South Bihar, for hosting this lecture. As I was just mentioning, the CUSB has taken initiative in establishing the Gaya chapter of IPA, and we welcome you all to the IPA family. The Indian Physics Association was founded in 1970. And we can get more information about it on the web page. Today, it has a presence also on the social media, keeping up with times. So as you just heard, we have a YouTube channel, but we also are visible on the Facebook and Twitter. So for information about the various IPA programs, past lectures, and the future events, please visit the web page. I'll put this comment also in the chat box, the web page address. So this is to give you what the IPA today is at a glance. So IPA has about 47 chapters all across India, as you can see here, spanning different parts, and about 4,500 members. The membership form is available on the web page. We have special student membership also. And what does the IPA do? Why should you join IPA? The IPA is kind of a major forum for the physicists in the country. It arranges special lectures, CV Raman being today's lecture being one of the series. It liaises with other national bodies, other societies, academies, gives the biennial awards for young and senior scientists, recognizing their contributions to the physics and the growth of physics in the country. It also has international linkages, agreements with various partner societies like APS, Institute of Physics UK, Italian Physics Society. It's also a member of AAPPS, that is the Association of Asia Pacific Physical Societies. So with this intersocietal agreements, the IPA members do enjoy certain privileges and benefits open to these society members. Taking advantage of the online platform, which has become recently available, particularly in view of pandemic, IPA has also organized several events in collaboration with international partners. The last year we had 2 webinars, one for young physicists and one for the addressing gender issue. IPA IOP has an exchange lecture series since 1998. So alternate years, people from India, the eminent scientists from India visits UK and vice versa. Recently, IPA endorsed the global effort for the role of physics in green economy. One of the major faces of IPA is the Physics News Bulletin. It's a quarterly bulletin, and it's again available online at our website. It does bring out many special issues from time to time, and some are featured here. This was a 2017 special all-women author issue. Recently, we also had an issue on S.N. Bose. And the special issue, the early part of 2021, was on Bibha Chaudhary commemorative issue. Bibha Chaudhary was one of the first woman Indian high energy physicists, and this issue featured the cosmic ray physics research over essentially the century, and as well as women in physics, particularly in India. The Physics News Bulletin has a few features. which may also be interest to the younger generation. We have a series called Meet the Physicists. So every issue features 4 physicists, young, senior, from across the places in India, and some entrepreneurs, telling you why he or she likes to do physics. And we also feature a profile of a department, physics department in the country. So if you would like to feature in Meet the Physicist, or feature, tell about your department, or your friends would like to tell us about it, please send a mail to the physics news address for doing that. The current office bearers for IPA are Professor S. Ramakrishnan, is the director of TIFR, who is the president of the IPA. Professor Tanushree Sahadas Gupta, she is director of SN Bose Institute, Kolkata, and she is a vice president. Myself, general secretary. Professor Samik Mandal from Delhi University, joint secretary, and Dr. Aradhana Srivastava is a treasurer. Another important wing of IPA is the Gender in Physics Working Group. This was established in 2017. This is to address the gender paucity issue in the physics community, particularly in India. And these are the current team members. This was actually provides a platform to address various issues related to gender parity. We also undertake, have initiated some of the mentoring programs, and there are specific workshops for the young women aspirant physicists, which are planned by the IPA Gender Group. With these few words, I would like to actually stop now and let you proceed with the present lecture. So the DAE CV Raman lecture series is supported by the BRNS. This was started in honor of courses led Professor CV Raman. We hold 5 lectures every year, and in different chapters, and on covering different subjects, with a hope of bringing the frontline research areas and the contemporary topics, the exciting things which are going on in the physics research, to the younger community, and with the hope that they will join this effort and will participate and make some exciting contributions to the physics research in the country. So thank you very much, and back to Dr. Puneet.
Thank you very much, ma'am. Thank you very much for this very nice introduction to IPA. And so actually now I would like to request my colleague, Professor Budhendra Kumar Singh, to kindly say a few words about the university and our department. And also I would like to request him to finally introduce our speaker and then invite him for delivering the lecture. So Professor Budhendra Singh, sir.
Thank you, Dr. Puneet. I have a small slide to share about the department. Is it possible?
Yeah, it should be possible. 1 minute. Ravindra, can you make him co-host? Yeah.
So first of all, good afternoon to all, and all the delegates here, Professor Jayaram sir and Vandana madam, everyone. On behalf of Professor Venkatesh Singh, today I will be introducing the Department of Physics. He is not well. Right now he is fighting with COVID, and for maybe we hope he will recover soon and join us. So this Department of Physics, which is a fairly new department, started in 2018. And within this short span of time, we have grown a lot, and we have many faculty members from different parts of the country, and they have a wide experience all over the world. The Department of Physics is headed by Professor Venkatesh Singh, who is a well-known nuclear and particle physics experimentalist, and all other faculty members are doing their best to improve and support the department. There are fairly a large number of projects which are running in our department. In this very short span of time, we were able to manage this. Now, coming on to the various characterization techniques that we have out of this, like XRD and all these good amount of uh, instrumentation and other characterization facility, along with the the facility for the synthesis of the condensed matter physics, like material science synthesis of the material and everything is available in our department, and we are always ready to collaborate with all the universities and other institutions of high importance. This department basically have two specialization program. One program is offered in condensed matter physics, and the other one is nuclear physics. Right now, we have only almost 17 PhD students, and we run BSc as well as MSc program, MSc in condensed matter physics and MSc in nuclear and particle physics. The Department of Physics currently run with 45 students. That is the maximum intake of the masters in the master's program. Out of that, 50% of the students go for the specialization in nuclear and particle physics, and 50% for the condensed matter physics. With this short introduction, now I would like to take this opportunity to introduce the eminent guest, like Professor Jayaram and Chengular, who has obtained his BTech in electrical engineering from IIT Kanpur in 1987. He then moved to Cornell University for his doctoral studies, and after he completed his PhD in 1994. Following this, he has also worked as a postdoctoral fellow at the Netherlands Institute of Radio Astronomy in Netherlands before joining the National Center for Radio Astrophysics in 1996. He is a fellow of Indian Academy of Sciences and National Academy of Sciences and Indian National Science Academy. He is also a recipient of Vikram Sarabhai Research Award in 2009 in field of space science for his contribution towards the outstanding contribution in dark matter in dwarf galaxy and characterization of interstellar medium using a giant meter wave radio telescope. The main research of Professor Jayaram is extragalactic astronomy, particularly study of nearby dwarf irregular galaxy, neutral hydrogen absorption in very high redshift galaxy, so-called damped lymph alpha system, and in general, studies of evolution of neutral hydrogen content of the universe. With this very short introduction, I believe that Professor Jayaram do not need any further introduction, because he is a so well-known personality in the field of nuclear science. So now I take with an honor, I would like to request Professor Jayaram and Chengular to deliver his talk for this Raman series.
Yeah, thank you very much, Professor Singh. I'd also like to thank the Indian Physics Association for arranging for me to give this talk, and also Professor Nanal and Professor Mishra for setting it all up and having things run so smoothly. So I'm sharing my screen now. I hope you can see it.
Yeah.
Yeah, thank you, Vandana. So, I'm going to talk about the radio perspective on galaxies and galaxy evolution. And, don't worry if you, very few of these words mean much to you, because I will actually try and explain as I go along what exactly all of this means. The telescope that you see in the background is one of the antennas of the Giant Meter Wave Radio Telescope, which is a facility built and operated by the National Center for Radio Astrophysics here in Pune. And all of the results that I would be showing you have come from this particular telescope. So I'll show you also a little bit, more about this telescope. I'll explain a little bit about how it works and the kind of things we do with it. But my focus will be on galaxies and galaxy evolution. But first, let me just start, by showing you this picture of the night sky. This is a picture taken in the southern hemisphere. The buildings that you see in the foreground are two buildings which house large optical telescopes, the very large telescope, so-called. It's in Chile. And you can see the night sky, above these buildings. And in the night sky, what is most prominently visible, I hope you can see it on your screens, is this band of stars across the sky. Right. And that band, of course, is the Milky Way. You can also, if you can see my cursor, you can perhaps see some blobs over here and over here. And these are actually two other galaxies. These are not the galaxy we are in. We are in the Milky Way galaxy. These are two nearby very small galaxies called the Large and Small Magellanic Clouds. These are dwarf galaxies, which I think Professor Singh alluded to also in his introduction. The Milky Way looks like a band because our galaxy is disc-shaped and we are sitting inside the disk. We are seeing the disk edge on, and therefore it looks like a band to us. And it's a band in which, you have millions, hundreds of millions of stars. Because there are so many of them, you can't distinguish them individually. They just look like this diffuse band of light. But what I want you to pay attention to now is that that band actually has some dark patches in it, right? And again, I hope you can see my mouse. Maybe it's running a little slower than my speech, but if you look carefully, you will see that that band has dark patches. Now, why are there these dark patches? Right? It's not dark because there are no stars over there. It's dark because there's something over there which is obscuring the light from the stars, which is preventing the light from reaching us. And what that is small, very fine dust particles. So they're basically clouds containing dust, clouds of gas containing dust, which is blocking the light from the stars in those regions from reaching us, right? And so, just from an optical photograph like this, it becomes clear that when we are talking about a galaxy, we are not just talking about a collection of stars, because typically when people say galaxies, you imagine that this is something which has many stars in it. And that's true, of course. But in addition, it has other things. And it has, as we have just seen, gas and dust. It also has magnetic fields. And as some of you may be aware, and as we'll also go through in this talk, it also has something called dark matter in it. The gas is something I would particularly like to focus on in today's talk. And it could be in any one of the phases that we know for gas. It could be either molecular, or it could be atomic, or it could be ionized, it could be a plasma, right? All these phases of gas exist in the galaxy. And in this talk, we'll particularly focus on one particular component of this gas, namely the atomic gaseous component of the gas. This component is diffuse and it fills the space between stars. And for that reason, it's also called the interstellar medium. In general, the interstellar medium is all of the stuff that fills up the space between stars. And we will look at one particular component of the interstellar medium, namely the atomic gaseous component. Now, if we ask the question, what is the composition of this interstellar medium of the ISM? The sun formed by gravitational collapse of gas in the interstellar medium. So, to a rough approximation, we can look at the chemical composition of the sun, and it's more or less basically the chemical composition of the interstellar medium, because the sun formed out of the interstellar medium. And that's something which we can do. We can study what is the chemical composition of the sun. It turns out more than 90% of the matter of the atoms by number is hydrogen, with about 8% helium. And there's a very trace amount of heavier elements than helium. And in astronomy, all these elements are called metals, right? So you have hydrogen, helium, and all heavier elements are called metals. And the metals are a very small, a very trace element. You can see it's about 0.2% of the total by number. And all the phases of the interstellar medium, whether you're talking about the molecular phase or the atomic phase or the ionic phase, they're all dominated by hydrogen because it is by far the most abundant element in the universe. So astronomers refer to the neutral atomic hydrogen as H1, H followed by the Roman numeral 1. And I just wanted to introduce that jargon because I have a habit of saying H1 instead of saying atomic hydrogen, and I just wanted to make clear that they mean the same thing. All right, so now let's just look at the role of H1, the role of atomic hydrogen in galaxies. And galaxies, actually, you get various kinds of galaxies, and they have different morphologies. And it turns out the fractional amount of H1, the fractional amount of gas in galaxies, varies with morphology. And I've shown you over here optical photographs of the three broad classes of galaxies. There are elliptical galaxies, which are basically elliptical in shape. They have no fine structure. They're very smooth looking. Then you have spiral galaxies, which is like our own galaxy. The Milky Way is a spiral galaxy. And these are flattened systems. They are disc-like. And the disc is not smooth, but it has spiral arms inside it. So there's a great deal of fine structure in these spiral galaxies. And then you have irregular galaxies in which there's no real shape as such. I mean, the stellar distribution is sort of patchy and irregular looking. And it turns out the gas content correlates quite tightly with the morphology. There's very little or no gas in elliptical galaxies. In large spiral galaxies, the gas is a small fraction in our own galaxy of the order of 10% of the mass in the stars. Whereas in small irregular galaxies and dwarf galaxies, the gas content could actually be much larger than the stellar content. The gas content could dominate the total baryonic mass of the galaxies. And the gas is important because, as I said when we were talking about the sun, the stars form out of the gravitational collapse of gas clouds. So the atomic hydrogen cools and collapses to form molecular hydrogen, which cools further and then collapses to form stars. And so therefore, as you would imagine, gas in general and atomic hydrogen in particular plays an important role in the evolution of galaxies. If I don't have any cool gas in the galaxy, then I don't have any raw fuel left for star formation. And so there will be no star formation activity. And I don't know if it's clear on your screens, but I hope you can see that if you look at the elliptical galaxy image, it's kind of reddish in color. And as we go to the spiral and then the irregular, the color gets more and more blue. And what's happening over here is that young stars tend to be blue in color, whereas old stars tend to be red in color. And the elliptical galaxy has no young stars because there's no ongoing star formation in it. So it has a reddish color. And by the time you get to the irregular galaxy, there's actually quite a bit of star formation going on in that galaxy. And so it has a lot of blue stars. And the galaxy as a whole is bluish in color. Right? So the gas is actually playing quite a critical role in determining what else is going to happen to the galaxy, the way in which it's going to form stars, the way in which it would evolve. So that's one of the reasons why it's interesting and useful to study the gas in galaxies. Another another sort of angle to this whole thing is that the atomic hydrogen is often detectable to much, much further distances than the starlight is detectable. So, from the center of the galaxy, you can see the stars out to a particular distance. And very often you can see the hydrogen out to much larger distances than you can see the stars. And so when, for example, you have galaxies which collide or interact or merge or are in a binary, the hydrogen, because it's further out from the center of the galaxy, is much more affected by the gravitational interaction than the stars. And so it's a very useful tracer of both galaxy structure and dynamics, as well as the interaction between galaxies. And I'll show you a particular example over here, where in the grayscale, the gray is just a photographic, it's an inverted photograph, so that darker means brighter. Of the stars in two galaxies. You can see these two galaxies over there. And the red contours are basically telling you where the hydrogen is. And they are contours of the brightness of the hydrogen. So the central contours are the brightest, and the brightness is falling as you go towards the edge of the galaxy. And these are two binary galaxies, which, if you looked at it in the optical, you would just see that there are two galaxies. They happen to be nearby on the sky. But that's about all you would probably say, that I have two nearby galaxies on the sky. But if you look at the hydrogen, you can see that the hydrogen is no longer actually confined to these two galaxies. You can see that there is hydrogen being pulled out of one galaxy, out of the smaller galaxy, and getting pulled into the larger one. The larger galaxy also has this large structure coming out from the other side of the galaxy. And so clearly these two galaxies are gravitationally interacting and merging. And the two-sided structures are very typical because these are all caused by the gravitational tides. And tides, as we know, are two-sided, so, right? So they'll produce something on the far side also. And so when you look at the hydrogen, it becomes abundantly clear that there are two galaxies which are interacting and will actually, if you model the system, finally merge with one another. Whereas if you just looked at it at the optical, it's far from, the story is far from clear that this is in fact what is going on. So these hydrogen observations are hence an excellent tool also to study galaxy interactions and mergers. So what you'd like to do, obviously, then is to measure or observe in some way the distribution of neutral hydrogen in galaxies. And clearly, there is a way to do it because I'm showing you a picture of the hydrogen distribution in galaxies. So how do we do it? How do we actually measure the hydrogen in the galaxies? So it turns out that atomic hydrogen, as you know, it consists of a proton and an electron, and protons and electrons have spins. And so there are two possible configurations for the hydrogen molecule in its ground electronic state. The spins of the proton and the electron could be parallel, or the spins could be anti-parallel. And these two configurations have slightly different energy. And so the atom could actually transition from one level to the other. And when it does so, it will be accompanied by either the emission or absorption of the photon. And since the energy difference between these two states is very small, it's only 6 microelectron volts, the energy is small, and therefore the frequency is actually quite low. It's in megahertz, it's 1420 megahertz, or equivalently, the wavelength of this photon is quite long. It is at 21 centimeters of wavelength. Right, so this is how you could observe hydrogen in the universe, because it actually emits a spectral line, and it emits that spectral line in the radio. There are other lines it emits in optical and so on and so forth, but this line is in the radio is particularly interesting because the atmosphere is actually transparent at these wavelengths. And I've just shown you over here, don't bother about reading the graph in detail. I'm just showing you the atmospheric transparency as a function of wavelength. And the takeaway from this is that there are actually only two windows through which electromagnetic waves from outer space can actually penetrate and reach the surface of the Earth. One window is the optical window, which is where the window through which the sunlight comes in and enables life on Earth. So the atmosphere is transparent at wavelengths around the optical wavelengths. And the other window is in radio wavelengths, right? So that's the other place where radiation from outside the Earth, from outside the extraterrestrial radiation could actually reach the surface of the Earth. So that means cosmic radiation from this 21 centimeter radiation can be observed using radio telescopes on the surface of the Earth. If the Earth's atmosphere was not transparent, we would have had to launch satellites to see this radiation, which would have been a very, very expensive proposition. But since it's detectable on the surface of the Earth, it's actually feasible at reasonable cost to build very large telescopes to observe these radio waves. So the first telescope with which this extragalactic, I beg your pardon, through which this hydrogen emission, it was not extragalactic, it was hydrogen emission from our own galaxy, was detected is the one which I'm showing you over here. And it's actually a relatively small antenna. It's a horn antenna, and it's poking out of a building in Harvard. And these measurements by Ewan and Purcell were one of a set of 3 measurements which were very closely spaced together, one in the US, one in the Netherlands, and one in Australia, which resulted in the detection of each one 21 centimeter line from clouds of gas in space. Now, it turns out that the probability that the hydrogen atom will spontaneously decay to the lower state, these two states which are involved in the emission or absorption of the H1 21 centimeter line are called hyperfine states. And supposing I have a hydrogen atom which is in the excited upper hyperfine state, the probability that it will spontaneously decay to the lower one is actually very small. The mean lifetime of the atom in the excited state is actually about 10 million years. So you'd think that the line might be weak, but however, it's fairly strong. And that is because hydrogen is such an abundant element in the interstellar medium. So because you have a very, very large number of hydrogen atoms in the interstellar space, you can actually detect this line even with relatively small antennas like the ones with which this first detection was made. As you can see, the antenna is roughly the size of a human being, maybe about 2 meters across. Modern radio telescopes are much, much bigger. I haven't shown you anything here to compare for size, but the diameter of this telescope over here is 45 meters. This is one of the antennas of the Giant Meter Wave Radio Telescope. And the way this telescope works is that it has a mirror. You can hardly make out the mirror. You can only see the backup structure of the mirror. And that is because the mirror is made out of a wire mesh, a very fine wire mesh. So since you're working with radio waves of wavelengths of 21 centimeters, any mesh with spacing which is much smaller than 21 centimeters will be perfectly reflective, right? So you put this wire mesh, which optically is transparent, but which is completely reflective in radio waves. And what it does is that it's a parabolic shaped reflector, so that radio waves coming parallel to the axis of the parabola get reflected and go to the focus. And at the focus, you have a feed antenna, like that, a small version of that giant horn that I showed you in the previous image. And that antenna converts the radio waves which are focused onto it into a voltage, into an electrical voltage. That voltage you amplify and you transport it to a central location for further processing. The GMRT doesn't have just one antenna. I'll show you in a moment. It actually has 30 antennas, and they all look at the same source at the same time. And the signals from all of these antennas are transported to a common location for processing. Right? So as I said, the antenna array consists of 30 dishes, each of which is 45 meters across, and they're very widely spread. They're spread across a region which is 25 kilometers in diameter. And the entire system has been designed, built, and is operated by NCR-AT-IFR. So the signals from these different antennas, as I said, are all transported to a common location, but there's a central location, and there they are then combined digitally. I'm not going to get into the details of this. I'll just mention the name of the technique. It's called aperture synthesis. So aperture synthesis techniques are used to convert these measurements into an image. So you actually end up making an image of the sky at radio wavelengths. That is, if you had a camera or if your eyes worked at radio wavelengths, this is what it would see. And the interesting thing here, though, is that the images have very high resolution. They have a resolution comparable to that of a telescope, which is 25 kilometers in diameter. Right? So it's very, very fine details that you can see of objects in the sky. It's as though you built a telescope which was 25 kilometers in size, as far as the resolution is concerned. I'm just showing you over here a picture of several of the GMRT antennas. And as you can see, they're all pointing in a particular direction, picking up radio waves from some particular source of interest. And I'm just showing you again, just one, as an example, an image made at radio wavelengths. And these are of supernovae remnants, I think. They're basically what happens when stars explode, where at the final stages of their evolution, they explode as supernovae, throwing out huge amounts of ionized gas, which then forms a shell, a spherical shell. And it's these shells that you're seeing in the radio. The shells emit bright synchrotron radio emission. All right, but now this talk is about hydrogen, and so I'm going to talk about two things. There are many, many things you could do, as I said, with hydrogen observations of galaxies, but I'll talk only about a couple of science cases. And the first one I want to do is to talk about hydrogen as a tracer of galaxy dynamics. Right. So what can I do with observations of galaxies in hydrogen gas to understand, better the dynamics of galaxies? So the hydrogen in the interstellar medium is in a disk, typically in galaxies, and this disk is not static. It usually is rotating. The gas goes in circular orbits around the galaxy center. And we are observing a particular spectral line from this gas, the hydrogen spectral line. And since the gas is moving with respect to us, we have a moving source. So obviously, whatever line it emits will be affected by the Doppler shift. So that means that the frequency that I measure at my radio telescope sitting over here is not going to be exactly 1420 megahertz, but it will be slightly larger or slightly smaller, depending on whether the gas is approaching or whether it's receding from us. Right? And so from this measured Doppler shift, as you know, you could actually measure the velocity of the gas. That is, you could measure how the rotation of the disk changes with position in the galaxy. And that, in fact, is the image which I had shown you earlier. So here we are looking at the hydrogen emission from a galaxy. But what I have plotted is not the intensity, not the brightness of the hydrogen emission. I've plotted over here the Doppler shifts that you get from different types of parts of the galaxy. So you can see that the Doppler shift, when I go from one end of the galaxy to the other end of the galaxy, is actually changing systematically. The blue indicates gas which is going away from me. The red indicates gas which is coming towards me. And green is at intermediate velocities. So you can see that's very systematic, right? That one half of the galaxy is going away from me, the other half of the galaxy is coming towards me. And that's exactly what you would expect if the galaxy was spinning, if the galaxy is rotating around its center. And the lines, the contour lines that you see over here are basically lines of constant Doppler shift, or equivalently lines of constant velocity, right? So all of the gas which happens to lie along any one particular line has the same Doppler shift or the same velocity, right? And from these contour lines, you could actually figure out how the velocity of this galaxy is changing as a function of distance from the center of the galaxy. And that is, you could make plots of the following kind. That is, you could look as a function of distance from the center of the galaxy. What is the rotation velocity, right? And this is what you get from that particular velocity field that I showed you. If I were to actually try and derive the rotation speed as a function of distance from the center, this is what you would get. All right, what would one expect to get? What should be the rotation velocity as a function of distance from the center of the radius, from the center of the galaxy? And, this is a very simple problem, things that you would have learned, in 10th or so, or maybe, probably in 10th standard is when you learned all these things, right? That planets, for example, if you look at things rotating, the classic example of things rotating is the solar system, right? And planets in the solar system, we know, follow Kepler's law of motion. And Kepler's laws of motion in turn follow from Newtonian dynamics and the fact that the mass in the solar system is concentrated near the center, right? And so in particular, if you ask the question, how does the orbital speed of planets change with distance? We know that it follows Kepler's third law. That is, the velocity decreases as the square root of the distance, right? V is proportional to 1 over square root of A, where A is the distance of the planet from the center, which is the sun. So if I were to plot it as a function of distance, I plot the orbital speed of the different planets as a function of distance from the sun. This is the kind of plot that I would get, right? It falls like 1 over square root of A. That fall, this particular curve is called a Keplerian curve, or a Keplerian change in velocity with distance. So if in my galaxy, most of the mass is concentrated near the center, this is how I would expect the orbital velocity to change with distance. The orbital velocity should fall like 1 over square root of the distance. Now, the galaxy, of course, is not a point mass. For the solar system, we could approximate it reasonably well as a point mass, and all of the planets as test particles. And that's not the case for galaxies. In real-life galaxies, the stars are not all concentrated at the center. They are, in fact, arranged in a thin disk, much like in our own galaxy. And I've shown you a picture over here of an edge-on galaxy to show you the disk of the galaxy. Now, the density of stars in the disk is not uniform when you go from the center to the edge. It in fact decreases exponentially. So the density is maximum, that is a number of stars per unit area or per unit volume, is maximum when I reach the center of the disk, and it falls exponentially as I go towards the edges of the disk, right? So this is the mass distribution that we have to deal with. We have to deal with a matter which is in a disk, and whose density is dropping exponentially from the center to the edge of the disk. It turns out, I mean, it's not as simple a problem as the solar system, but it is tractable analytically. And you can actually plot what should be the expected orbital speed as a function of distance for a disk of that sort. And that's what I'm showing you over here in the blue curve. So this is a blue curve, shows you the expected rotation velocity as a function of distance for such a disk, for an exponential disk. And you can see that what happens is that the rotation velocity increases first as you go from the center outwards, reaches a maximum, and then begins to fall. And just for comparison, I've shown in that dashed line what the rotation velocity would be for a Keplerian mass. That is, if I took all of the mass of the galaxy and I sort of squished it into a point at the center, and then I plotted the orbital speed for that, what I would get is the green dashed line. And you can see that at large distances, the two curves begin to overlap. And that's understandable, because if you're far enough away, the details of the mass distribution don't matter. It pretty much begins to look like a point mass to you, and you begin to see this decline in velocity. So in a sense, it does, the details of the mass distribution matter when you're close to it, but if you get far enough away from the mass distribution, you would expect that the rotation velocities would begin to fall. And if you're far enough away from it, should begin to fall in a Keplerian fashion. All right, so is that what we see for galaxies? And as you saw from the rotation curve, that's not what we see. Galaxies typically have what look like flat rotation curves. That is, the velocity remains constant. It increases from the center as you go out, but then at some point it stops increasing, but it doesn't decrease either, right? It just stays more or less constant. So they're kind of flat. They remain constant almost all the way to the last measurable point in the galaxy. That is, so what this is telling us straight away is that the total mass of the galaxy cannot be concentrated at the center, right? Because if it were, then I should have seen the velocities begin to fall. On the other hand, all the observed baryonic material is concentrated at the center. The stars, which in spiral galaxies dominate the total baryonic mass, are all at the center. The gas density begins to fall as you go further and further out. And so the contribution to the mass of the gas at large distances is actually negligible. And so, even if I put both the gas and the star mass together, I would not expect a flat rotation curve. I would definitely expect the velocities to be falling. The only way to explain these observations, well, actually, there are two ways to explain the observations, but the most straightforward way to explain the observations is that there's a third component to the galaxy, which I am unable to see. It has a third component, which we could call a dark component. And this component is much more distributed. It's not concentrated at the center, because were it to be concentrated at the center, the rotation velocities would fall, right? So it's not concentrated at the center. It has to be much more diffusely distributed than the stars or the gas, right? So it kind of forms a halo around the galaxy. So these are what would be called dark matter halos. And it turns out that this component, if you work out what is the mass of the stars, the mass of the gas, and then the mass in the dark matter, which is required to produce these rotation velocities, it'll turn out that the total mass of the galaxy is completely dominated by the dark matter. So the galaxy that you see is in some sense like the tip of the iceberg. And what you're not seeing, the dark matter, is in fact the dominant component of the galaxy. I had mentioned there's one more way to interpret these observations. I won't get into it in detail, but the way is basically to assume that Newton's laws don't apply, that the Newtonian physics is wrong and you need some other physics. And we are not talking here about special relativity or any of those, because the velocities, as you can see, are very, very small compared to the speed of light, right? You're talking about 30 or 40 kilometers per second, maybe 100 kilometers, a couple of 100 kilometers per second at the most. So you are talking about a fundamental sort of change to the laws of physics, which manifest perhaps only on very large length scales. So, that's an idea that some people work with. All right, so here I sort of just introduced this idea of using hydrogen to study the dynamics of galaxies, to try and understand the nature of galaxies. But what people actually do these days was, much more sophisticated than what I've shown you. I've just sort of shown you things that we have known for quite some time and which are no longer really where the research is happening. So what thing people study these days now are what is the density distribution of the dark matter. That is, I've assumed I know from these observations that the dark matter has to be much more diffuse than the gas, but I haven't yet understood how does the density of the dark matter decrease as I go from the center to the edge of the galaxy, right? And that is something which you would like to understand, because it also will depend on our models of galaxy formation and evolution. Right, so that's things that people study. How does the density distribution of the dark matter depend on the distance from the center? We are talking about a dark matter halo. What is the shape of the halo? To start with, people assumed that the halo was spherical, but now you can actually try and start to probe. Is that a correct assumption? Are halos typically spherical, or are they oblate, or what kind of shapes do dark matter halos typically have? And, we are working all of this with gas which is rotating around the center. You could ask the question, what is the origin and the evolution of the angular momentum in galaxies, right? Why do they spin to start with? What determines the rate of spin? How will this evolve with time, and so on and so forth? So these are all questions that people could ask using neutral hydrogen observations, and they're all questions that people are working with using GMRT data. But what I want to do now is to move on to another, quite different topic. And I want to talk about gas and galaxy evolution. I've sort of hinted from the start that the gas is going to play an important role in galaxy evolution. And I want to talk about that in a little bit in this remaining part of my talk. Right. So, but first, what I need to remind you, probably all of you are aware of it, but it's worth just bringing it back to the front of our minds, that light travels at a finite speed. So that means that when we are receiving on the Earth sunlight, it's actually light that was emitted by the sun 8 minutes ago. So in a sense, we observe the sun the way it was in the past, the way it was 8 minutes ago. If you look at our nearest star, the light emitted by that nearest star reaches us after about 4.3 years. So that means that we are seeing the star as it was in the past 4.3 years ago. Whereas if I look at some very, very distant galaxy, the light from it could take as much as 1 billion years to reach me, right? So then what I'm observing when I look at that galaxy is not the galaxy as it is now. I'm observing as the galaxy as it was in the very, very distant past, the way it was 1 billion years ago. Right. So in that sense, telescopes are like time machines. If I look at distant objects, I'm actually probing the earlier phases of the evolution of galaxies. So as I look at more and more distant objects, I would typically begin to see earlier and earlier populations. Right. So that allows one sitting here at the Earth to study observationally the evolution of galaxies. The other thing I wanted to remind you all was that as we all know, the universe is expanding. And so that means that the wavelength of the photon that I receive on the Earth is going to be longer than the wavelength that the photon had when it was emitted. Or in other words, the light is redshifted. Right? So the increase in the wavelength between what it was when it was emitted and what it was when I received here. So for example, maybe there was a hydrogen gas cloud in the very distant universe. It emitted radio waves at a wavelength of 21 centimeters. But by the time it reaches me, it has lengthened to 30 centimeters, right? So that wavelength increases. And that increase in the wavelength is quantified by what is called the redshift Z. Right? And this redshift Z is a measure both of the scale by which the universe has expanded. So if it was from 21 to 30, it tells me how much the universe has expanded since the photon was emitted. But since the photon has been traveling also for all of this time, it's a measure also of the time elapsed since the photon was emitted, right? So if I know the expansion scale, the rate of which the universe is expanding, I could also tell you how much time has elapsed since the photon was emitted, right? Because I know how much time it takes for the expansion to take the photon from 21 centimeters to 30 centimeters. So just by measuring the wavelength, the redshift of that hydrogen line, I could measure the time. I know how much further back into the past one is looking, right? And so this allows one, therefore, to study galaxies further and further into the past. The only thing you need is a telescope that is sensitive enough to detect these hydrogen emission from these very distant objects, and that is a problem I'll get to in a moment. Right? But before I get there, let me just remind you again about the role that gas plays in galaxy evolution. The gas collapses to form stars. For example, in the spiral arms of galaxies is typically where this activity happens very vigorously. And so I'm showing you over here an image taken with the Indian Astrosat satellite of a nearby spiral galaxy, NGC 2336, and you can see the very prominent spiral arms. And that's because these wavelengths are very sensitive to young stars. And so what this image is showing you is where the young stars are in this galaxy. And the young stars are predominantly in the spiral arms. Right? It's telling you that the star formation is sort of dominated by the spiral arms. It happens dominantly in the spiral arms. So what is happening over here is that the gas is collapsing and forming stars. And as the galaxy evolves, the gas would get gradually depleted. And finally, when there's insufficient gas left in this object, it would stop forming stars. And so that's what you would imagine would inevitably happen to all galaxies, unless there is some means by which you're continuing to put fresh gas into the galaxy. That is, there is some way in which gas is flowing from this intergalactic space into the galaxy. Right? So if you are able to look at all of this, we are able to sort of understand the way in which star formation evolves with time, the way in which the gas content of galaxies evolves with time. We can begin to understand the way in which these galaxies build up. Are they built up? I can consider a couple of cartoon models that maybe you have one gas cloud and it doesn't interact with anything. It just keeps collapsing, forming stars until the gas is over. And so basically that's all you have. At some point in time, you found gas clouds, and then they just, each one independently evolves, forming more and more stars until the gas is over. Or at the other extreme, maybe there's gas continuously flowing into galaxies. There are other processes going on, and this galaxy formation process is continuing, continuously over the age of the universe. Right? These are kind of models you could build, and theorists build these models and tell you how they believe things are happening. But what would be good would be to try and get an observational handle on it so that one can constrain which of these models is actually the truth. So let me show you here an observation taken from optical data about the rate at which galaxies are forming stars as a function of age of the universe. So the age of the universe is shown on the upper horizontal panel in gigayears, at gigayears 10 to the 9 years, billion years. So, and the corresponding redshift is shown at the bottom axis. And so you can see at high redshifts or in the very early universe, there's not a whole lot of star formation going on. Then at about redshift somewhere between 1 and 3, there's a huge amount of star formation going on. And then at redshifts lower than 1, that is in the more recent universe, the star formation is gradually fading out. Right? So the star formation rate of galaxies in the universe has not been uniform. Right? It was low to start with. It peaked at about redshifts of 1 to 3, that is look back times around 8 to 10 gigayears ago. And after that, it has been steadily declining. And you could ask the question, why has this happened? For example, let's ask the question, why did the decline happen? Does the decline in star formation happen because of depletion of gas? Right? That's a question you could ask. Are these galaxies no longer forming stars so accurately because of depletion of gas? And that is something then you could try and answer observationally by measuring the gas content of these galaxies. Now, there's a problem here. The problem over here is that the hydrogen emission from distant galaxies is actually extremely weak. And even if you use large state-of-the-art telescopes like the GMRT, it's very, very difficult to detect it beyond the local universe, right? There's another way in which you could observe hydrogen, and that is to use lines which line the ultraviolet, Lyman alpha. So for example, if I excite the hydrogen atom from its ground state to the first electronic state, then that's basically going to absorb a Lyman alpha photon, which is at a wavelength of 1216 angstroms in the ultraviolet. Right. So if I happen to have gas, a lot of gas in the early universe, and I have something which is emitting bright UV emission further back in time, maybe an earlier galaxy or a black hole which is accreting matter and is therefore very bright in ultraviolet light, that light will get absorbed by the intervening hydrogen clouds, and I would be able to measure how much hydrogen there is in the universe by the amount of absorption of Lyman alpha that happens. Now, these are measurements which are easy to make only for objects at high redshifts, at redshifts greater than 2, because at redshifts greater than 2, the Lyman alpha redshift, the Lyman alpha wavelength will also expand. And so something which absorbed at 1216 angstroms, by the time I receive it, it'll be at a longer wavelength. And at redshifts greater than 2, that wavelength lies in the optical window. And you remember I said optical is one of the two windows in which extragalactic electromagnetic waves can reach the Earth, right? So if it's beyond a redshift of 2, I can actually see those objects with telescopes on the Earth. So at redshifts greater than 2, one can actually make measurements using Lyman alpha, but below 2, you can't, right? And so in fact, there's very, very little known about the atomic gas content of galaxies between redshifts of about 0.2, which is the outer limit of where you can get with a radio telescope typically, and a redshift of 2. And that's what I'm showing you over here. We have redshift on the horizontal axis, and on the vertical axis is some measure of the neutral hydrogen content of galaxies, right? And you can see that there's a large range in the middle between redshifts of about 0.2 and 2, where there are some measurements, but they have very large error bars, and they're very sparse compared to the way in which there have been measurements elsewhere. And that's because at redshifts greater than 2, you could use the Lyman alpha and you could get reasonable measurements. At lower redshifts, you could use the hydrogen 21 centimeter line and get measurements, but it's very difficult to do in this intermediate regime. So what can you do in the intermediate regime? So in that intermediate regime, where you could use the following fact, that a radio telescope actually observes not one point at a time, it observes all the objects within its field of view, right? So that means at any one instant of time, the volume of space observed by a radio telescope contains a large number of galaxies. So then even though you don't have the sensitivity to detect an individual galaxy, you could measure the average hydrogen content of all of these galaxies by aligning their emission together and adding them up. That's called stacking. So basically, you need to know the three-dimensional position of all of the galaxies to be stacked. If I know exactly where all of the galaxies are, I know exactly where the hydrogen line from each one of them, what frequency it should come at, from what point in space. I can align all of them up, I can add it up, and I should be able to make a detection. And that's what I'm showing you over here. That's supposing, for example, I have 3 galaxies. Which are at within my field of view, but at slightly different redshifts, right? So the hydrogen line from these 3 galaxies should come at the arrows marked Z1, Z2, and Z3, because those are the redshifts of these objects. And as you can see, you can't really see anything over there because you don't have the sensitivity to see the line. But what I could do is that I can align all of these spectral lines together and add them up. That is, I shift the spectra so that the bit corresponding to the hydrogen line is all at the same space, and then add it up, and then you can actually see the signal. That's because the signal adds up coherently, whereas the noise in the spectrum will not add up coherently and will gradually average down. So if I have a large enough number of galaxies, even if I can't detect any one of them individually, I can certainly make a statement about what is their average hydrogen content. And so this is a program which has been running at the GMRT for a long time. And I'm showing you here one of the very early results from that program, where we looked at a particular field of galaxies in which there were about 120 galaxies within the volume that we had imaged. And you need to know the 3-dimensional positions of the galaxies, which we obtained by sort of obtaining their optical spectra. And there were 2 problems over here in really trying to sort of get a very strong signal. And this two problems are the following: that one, you have a very small number of galaxies, only 120. And second, that's because the volume you are probing with the GMRT is actually relatively small. And the second problem is because you have a small volume, the number of large galaxies that you'll have in this volume is actually also small. So most of these 120 galaxies are actually smallish, dwarfish kind of galaxies, which don't have a whole lot of hydrogen. So even when you stack them together, you don't have a very strong detection. So we had sort of the hint that there is some emission at the right place, and that allows one to constrain the average gas content of galaxies, but it didn't actually lead to a statistically robust measurement. Now the situation has changed quite dramatically. This was in 2007. And to explain why the situation has changed dramatically, I have to say a little bit about what has happened to the GMRT. The old GMRT, the one with which those earlier measurements were taken, I told you that all of the signals are combined together electronically. That electronics had a relatively narrow bandwidth. It had a bandwidth of only 32 megahertz. And that meant that you could observe only a small slice of the universe at one time. The redshift slice that you could observe was only 0.03 at redshifts of around 0.3, right? You could observe only a narrow slice at any one time. And because of that, the observation covered a relatively small volume, only of the order of about 100 galaxies, many of which were small and intrinsically faint. So if you were able to actually observe a very large number of galaxies at a time, you could observe a large, and if you could observe a large instantaneous volume at a time, it would make a huge difference. And that's indeed what is now possible with the upgrade to the GMRT, which has just recently been completed, and which also, again, was completely done in-house. And I'm just showing you over here how the frequency coverage of the old telescope compares to that of the new telescope. The old telescope frequency coverage, we have frequency on the horizontal axis, and the frequency that you could observe at any one given time with the old telescope is what's shown in the blue. And what is shown in the kind of salmon pink is what you can observe with the upgraded telescope at any one time. So you can see straight away that there's a huge increase in the number of frequencies and the bandwidth of the telescope. And that means you can observe a very large redshift interval at one time, or equivalently a large volume of space at one time. And therefore you can add up together, you can stack up together the emission from a large number of galaxies at a time. And this also, of course, has an effect on the sensitivity of the telescope. The broader you make the bandwidth of the telescope, the more sensitive it is. I won't get into details of this figure over here. It's just comparing the upgraded GMRT to other radio telescopes around the world. And the take-home message from this is that at its frequencies of operation, the GMRT is one of the most sensitive radio telescopes in the world after its upgrade. And it'll continue to keep that position until the next generation telescope, which what's called the square kilometer array, comes along. Right? So when I increase the bandwidth to 400 megahertz, the sensitivity increases, but not for spectral lines. It increases for continuum emission, for emission which is 400 megahertz wide. When I have a spectral line, it doesn't actually change the sensitivity. But because you can observe such a large volume at one given go, it makes a big difference to studies like the ones I'm talking about, where you do stacking. Right. So let me now end by showing you two results which have come out recently from such stacking experiments. The one is first one is at intermediate redshifts done by Apurva Bera, whose photo I've shown you over here, a student who's just recently finished his PhD at NCRA. And what he did was he was able to stack together spectra of 445 galaxies, right? So now there's a much bigger sample of galaxies at a higher redshift than the one I showed you. I'd shown you at about 0.2. This one's now at 0.34. And because of all of the improvements that I just went through, you actually are able to make a very convincing 7 sigma detection of the H1 emission from this galaxy. And it's the first statistically significant measure at these redshifts. And it shows that the galaxies are much, much more gas-rich than local galaxies. So at a redshift of 0.34, these galaxies had a whole lot of gas. From the same observations, you could actually also measure the star formation rate. You could do that from the radio continuum, from the synchrotron emission from these galaxies. I won't get into the details. But when you do that, you find that the star formation rate in these galaxies is also large compared to local galaxies. And that's something that we had seen before, that between redshifts of 1 and 0, the star formation rate is evolving actually. So from these observations also, you can measure that evolution. And for this exact same sample of galaxies, you could measure the star formation rate. And what you get when you do all of this is you could measure the time it takes for all of the gas in the galaxies to form stars, because I know the amount of gas it has. I know the rate at which the gas is forming stars. I can compute the ratio, which is basically telling me how long it'll take for all the gas to become stars. And it turns out that the gas depletion time is similar to galaxies in the local universe. So these galaxies are kind of sort of, just chugging along. They don't need to accrete a whole lot of gas. With the amount of gas that they have, they can just gradually continue to evolve, and they will become the galaxies that we have today. So that's what's happening at about redshifts of 0.34. We could also push to still higher redshifts, to still larger distances, earlier epochs in the universe. And this is a paper which came out a couple of years ago now, at a redshift of 1 now instead of 0.34. Here, the number of galaxies that have been averaged together is much larger. It's about 7,500 galaxies. And even though you're working at such a large distance, there's still this very, very clear detection of the average H1 emission. And what one is able to say from this is that the galaxies are much more gas-rich than the local galaxies. And similarly to what we had done at redshift 0.34, from the same observations, you can also measure the star formation rate. And here is the surprise. The star formation rate is such that the gas depletion time is extremely short. It's only about 1 billion years. So at about this redshifts about 8 or 9 billion years ago. And at these redshifts, these galaxies have only enough gas to produce stars at that rate, at the rate at which they're producing stars. It's sustainable only for about 1 billion years. And that's what the observations are very directly telling you. And so what it indicates is that what is likely to be happening is that this is around probably the epoch at which the gas in the galaxies is no longer increasing. There's no longer much accretion of gas in the galaxies. So it's sort of, this is the last epoch at which they have enough gas at which they can form stars at this very, very rapid rate. But it sort of runs out of that fuel within 1 to 2 billion years. And then it has to switch into this mode in which it's much, much more slowly forming gas into stars, the mode which we are seeing in galaxies around us today. So that's where I'd like to stop. I think there are time for questions. So thank you for your attention, and I'd be happy to take any questions you have.
Thank you very much, sir. Thank you very much for this wonderful talk on galaxy evolution and your observations using atomic hydrogen spectral lines. So students have some questions. So Aditya Behra is asking, can we know why the galaxies have different structure form? Maybe he's talking about shape.
Yeah, why it's actually a very interesting question, and it will have to do with the way in which galaxies evolve. Now, there are multiple, I'll just sketch some processes for you which could lead to galaxies of different shapes, right? And but the truth, of course, is more complex than any of these. So, for example, supposing I have a gas which is sort of I have a rotating gas cloud, which why it's rotating, let's not worry about right now. But supposing it's rotating, typically these things rotate because of tidal interactions in the very early universe. Because of mutual tidal interactions between halos in the early universe, they spin each other up, right? So to begin with, these things have a little bit of angular momentum. So if I have something like gas which is collisional in such a spinning object, it'll actually settle into a flat disk. That's pretty much also why, if you look at the solar system, you can see the planets are in a disk, right? That's because the gas cloud of which the solar system formed out of had angular momentum, and naturally it will slowly flatten into a disk. So you'll get these disk-like galaxies. Supposing, on the other hand, I take disk-like galaxies and I make them merge and collide with each other, that actually begins to disrupt, these flat pancake-like shapes. It heats up the gas, and then it begins to form a structure like elliptical galaxies, in which the stars have a whole lot of random motion. Instead of their energy being in sort of regular orbital motions, it's now in sort of random motion, much like the random motion in a gas, and it sort of an equilibrium configuration are these elliptical shapes with hot gas distribution. There are, so as I said, I'm not actually going to tell you the whole story. It's much more complicated than this, and it's not also fully understood. But you can see that different processes are going to end up producing galaxies of different kinds and different shapes. And all of these processes are at play in the cosmos, and they end up producing, the zoo of galaxies that we see around us today.
Thank you, sir. Sir, the next question is from Rituraj Patnaik. He wants to ask, the hydrogen which collapses to form star, whether it is atomic hydrogen or molecular hydrogen?
Yeah, no, that's a good question. So it's typically molecular hydrogen. As the hydrogen sort of cools and collapses, it'll eventually form molecular gas. And then the molecular gas further cools and fragments to form the gas clouds. So yes, there would be this intermediate phase of molecular gas.
I see. Thank you, sir. Sir, next question is from Anshuman Mishra. He wants to ask, if hydrogen is so abundant in space, do we use it as a source of energy?
Yeah, well, you'll have to get it from space to Earth, right? And that will take a fair amount of energy to transport all of that hydrogen from space to Earth. And I don't think that would work out. And the other thing to really bear in mind is that space is huge. That the volume density of hydrogen atoms in space is extremely small. So even though there are large amounts of hydrogen in space, they're distributed over a very, 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 very large volume. So again, it won't be energetically favorable to go around trying to collect it. It's much better to try and collect energy from places in the universe where nature has already concentrated it for you, like in the sun, right?
Thank you, sir. Sir, he has another question. He wants to ask, is a circular galaxy dying? So maybe
I'll take it as meaning that are the disk-like galaxies? Are the disk-like galaxies, are they forming stars? Are they not forming stars? And as a broad generalization, the disk-like galaxies typically are still forming stars. Whereas the ones which are spheroidal in shape are usually not forming stars.
Sir, Vishwarup Das has a question. Why gas forms stars only in a certain positions or certain locations?
Okay, for example, I had said that star formation is concentrated in the spiral arms. And that has to do with the way in which the spiral arms themselves are formed. The spiral arms are regions where there's a higher density than average of the gas. And there's also sort of motions of the gas. I mean, the whole thing perturbs the rotation of the galaxy. For all of these reasons, these are areas in which the gas actually tends to be less stable, where it is more easily able to fragment into denser and denser objects and form stars. You could also, for example, imagine a situation where, for example, we have some stars in a gas cloud already, and maybe some of these stars have evolved sufficiently and they explode as supernovae. If I have a massive star, after a certain amount of time, the hydrogen in its core is exhausted, and it goes through a cycle of nuclear burnings. But at some point, it basically runs out of fuel, and the star basically undergoes a violent kind of end and a violent death, which involves shooting out its outer layers at very high speeds, thousands of kilometers per second. And this, of course, is much larger than the sound speed in the gas cloud. So this will drive shock waves through the gas cloud. And these, in turn, could lead to further star formation, right? So you could have these triggered sets of star formation that once I form a bit of stars, then when they explode as supernovae, they trigger the next set of star formation. When those trigger stuff, they trigger the next set, and so on and so forth. So for all of these reasons, star formation is not necessarily uniformly distributed in the galaxy, but it happens at discrete locations.
Sir, Narendra Shah has a question that what kind of law or mechanics is at work at larger distances?
Okay, so if you're really interested in that, let me try and remember the name. 1 minute. It's called it's called MOND. It's called Modified Newtonian Dynamics. So basically they suggest at very, very low accelerations, the dynamics deviates a little bit from Newtonian dynamics, and you would imagine that that idea may not take you very far, but actually it turns out that it's a little hard to disprove with existing data. It's lived for much longer than one might imagine. So if you're interested in look it up, it's called MOND, M-O-N-D, for Modified Newtonian Dynamics.
Thank you, sir. Sir, Ankita has a question. Why a star formation cannot take place without cool gas?
That's because the gas has to collapse to form very dense. The gas has to become very dense. Only after that, you could trigger the nuclear reactions and so on in it, right? So you have to start with a fairly dense gas cloud, and then because of further gravitational instabilities, the thing has to get further and further compressed. So, but to start with, the thing you need is a fairly dense gas cloud. And for things to become dense, they have to be cool. If it's hot, you can't actually compress it to those small volumes, right? So as things cool, as the atoms cool, their random velocities will become smaller and smaller, and so they will settle closer. So for example, if I was in a galaxy where the gravity is maximum towards the mid-plane, they'll get closer and closer to the mid-plane of the galaxy, forming a denser and denser object, until finally, some kind of gravitational instability gets triggered in it, causing it to fragment further and form stars.
Okay, sir, there is a question on YouTube, and that is, can we detect the radio emission coming from particle showers that develop in the terrestrial atmosphere as a result of the interaction of ultra high energy cosmic rays, gamma rays, and neutrinos?
Yes, I believe you can. I don't know a whole lot about it, but yes, you can. And I think that there are radio telescopes, particularly those which work at quite low frequencies, which study this phenomena.
Thank you, sir. Sir, so mostly, yeah, the other questions are very similar to what I have already asked you. So with that, we would like to thank you very much for this really wonderful talk. And I'm sure our students will be inspired to take up research in astrophysics. And now they also know that who they have to follow if they wish to make strides in this field. So I would like to thank and I would like to express my gratitude to IPA and Professor Vandana Nanal for providing us this opportunity to host this wonderful lecture. And we look forward to further opportunities to host more such events, especially in physical mode once the pandemic is over. And I would like to thank Mr. Ravindra Shinde from IPA for his technical support related to Zoom platform and for live streaming on YouTube. And I would also like to thank Professor Venkatesh Singh, the head of our department, for his continuous encouragement and starting the IPA activities at our university. And I hope he gets well very soon. And I would like to thank all the faculty members of our department for their help in organizing this event. And finally, I would like to thank all the students of CUSP and the participants for their gracious participation in this webinar. So thank you very much. Thank you, sir. Thank you very much again for this wonderful talk.
Yeah, thank you so much.
Thank you, sir. So with this, we can now close the webinar.
Yeah. Okay,
thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you. Goodbye.